Okay, so in this lesson we're going to talk about second order linear ordinary differential equations. And so we first need to start off by defining what ordinary means. Ordinary means that the differential equation includes one independent variable and its derivatives. So for example, in most cases you'll see the variable as y, and you'll see a differential equation that looks something like 4y prime equals y. And there won't be any other variables except for y. Linear, however, has a different meaning. A linear equation signifies that constant multiples and linear combinations of solutions give rise to different solutions. So, as I finish writing this, we'll give you an example. An example would be 4 equals yx. So, some solutions of 4 equals yx include 1, 4, 2, 8, and 3, 12. Now let's first look at constant multiples. So a constant multiple would be 2, and 2 times 1, 4 equals 2, 8. I messed up there. So as 2, 8 is also a solution, then this verifies that constant multiples work. So 1, 4 plus 2, 8 equals 3, 12. And 3, 12 is also a solution, so this verifies that linear combinations of solutions give rise to different solutions. And so therefore 4 equals yx is linear, or y equals 4x is linear, my bad. So now that we've looked at some definitions, let's look at the standard form of a second order linear ordinary differential equation. So the standard form is y double prime plus p of t y prime plus q of t y equals rt. And so, since this is a linear differential equation, then it also abides by the principle that linear combinations and constant multiples of solutions give rise to different solutions. So let's say you had the solutions of y1 and y2. So you can write y1 and y2 as C1Y1 plus C2Y2, and this would form another solution given that r of t equals 0. So here I'm writing this down for you, C1Y1 plus C2Y2, and this will be another solution to the differential equation if y1 and y2 are already solutions, provided that r of t equals 0. So when r of t equals 0, this means that the second order differential equation is homogeneous. Alright, so let's talk about the general solution to a second order differential equation. So the general solution also takes the form of y0 equals C1Y1 plus C2Y2. But a general solution only holds if you're given an initial time t0, and you substitute that into your general solution, and you can solve for C1, right? But then when you differentiate your general solution and you substitute that same initial time in, you can solve for C2. So basically, if you're given an initial time, then you should be able to take that time, substitute that into the general solution, substitute that into the derivative of the general solution, and solve for C1 and C2. So if you can't solve for C1 and C2, given that initial time and that solution that you have, then it's not a general solution. So how do you know if you can solve for it? Well, you can write down this linear system of differential equations. So that system would be C1 y1 of the initial time plus C2, y2 of the initial time equals y0. And then you have C1, y1 prime of the initial time plus C2, y2 prime of the initial time equals y0 prime. And so like I said, if you substitute the initial condition in to both the function and its derivative, you should be able to solve for C1 and C2. And if you can't solve for that with the general solution that you have and the derivative of it, then it's not a general solution. So let's write this system in matrix form. So we're writing that matrix, and the first row is going to be y1 of t0 and y2 of t0. And the second row is going to be y1 prime of t0 and y2 prime of t0. And when you multiply that by C1 and C2, you should be able to get y0 and y0 prime. And so how do you solve for C1 and C2 within this matrix equation? Well, you solve for it by inverting the 2 by 2 and multiplying that inverse onto the other side. And the only way that this can be done is if the determinant of the 2 by 2 is not equal to 0. Because if it is equal to 0, then when you multiply it trying to solve for the inverse, you end up getting a non-existent inverse. So the inverse only exists when the determinant is not equal to 0. And when the inverse exists, you can solve for C1 and C2. So when you can solve for C1 and C2, that means you have a general solution. So, like I said before, if the determinant of that 2 by 2 matrix, y1 of t naught, y2 of t naught, y1 prime of t naught, and y2 prime of t naught is not equal to 0, then that means you can solve for C1 and C2. And so if you can solve for C1 and C2, then that means that C1Y1 plus C2Y2 is, in fact, a general solution. So this determinant of that 2 by 2 matrix, that's called a Wronskian. So the Wronskian is a function of the initial time. And when you have those two solutions to that second order differential equation, and you're trying to see if those two solutions combine together form a general solution, you can take the determinant of that 2 by 2 matrix along with an initial condition and see if you can solve for C1 and C2 given any condition. And I forgot to write the initial time into that notation there, but remember that the Wronskian is a function of the initial time. And so if you've forgotten how to find the determinant of a 2 by 2 matrix, it is, in this case, y1 of t naught times y2 prime of t naught minus y2 of t naught times y1 prime of t naught. And so